After thousands of years shaped by colonial history, many parts of Africa were left with outdated infrastructure. Into this landscape, China introduced a new wave of development in Kenya, bringing advanced technology and modern engineering to build a massive railway system. Elevated tracks now stretch across open savannas, kilometer-long viaducts cross difficult terrain, and modern operating technology, never before seen on such a scale in Africa, became part of the project. Tens of thousands of workers, heavy machinery, and billions of dollars in investment were mobilized to complete the standard gauge railway in just a few years. An ambitious project, widely seen as capable of reshaping Kenya's economic future. So how did China build this railway? Why was it willing to invest so heavily in Africa? And what truly lies behind this mega infrastructure project? Let's explore with Mandarin Tech. Before China's involvement, Kenya's railway system was largely a legacy of British colonial rule. The infrastructure had deteriorated over decades. Trains operated slowly, and transportation costs from the port of Mombasa into inland East Africa ranked among the highest in the world. Seeing this massive infrastructure gap, China proposed building a modern railway network as part of the Belt and Road Initiative, turning Africa's development needs into a strategic opportunity for itself. In 2014, construction of the standard gauge railway began, with a loan of about $3.8 billion from the China Exim Bank. The state-owned China Road and Bridge Corporation was responsible for design, construction, and technology deployment. In less than 3 years, the 480-kilometer Mombasa to Nairobi railway officially opened in 2017, complete with Chinese locomotives, signaling systems, technical standards, and workforce training programs transferred alongside the infrastructure. Despite investing billions of dollars, China's interest was not focused on short-term profit, but on long-term strategy. The loans generate financial returns over decades. Chinese companies gain overseas projects while exporting steel, machinery, and railway technology. In other words, China was not simply building a railway, it was building economic influence, supply chains, and geopolitical presence in one of the fastest-growing regions of the world. First, China's top engineers developed the overall concept for the railway and began conducting on-site terrain surveys. Engineers and planning experts carefully analyzed Kenya's landscape to understand the challenges of the route. Using satellite data, aerial survey aircraft, and modern measuring equipment, they identified the most efficient path to reduce construction costs while minimizing environmental impact. In the end, they finalized a railway line stretching 472 kilometers, running from the port of Mombasa to the capital city of Nairobi. Most sections of the line were built as elevated railway structures, ensuring stable foundations and allowing trains to operate safely and continuously across different types of terrain. After the route had been defined, the next challenge was to reshape the terrain along the entire construction corridor. In Kenya's sandy and uneven landscapes, hundreds of bulldozers and grading machines were deployed to cut down high mounds while filling in lower areas. The goal of this stage was to create a stable and balanced surface strong enough to support heavy construction equipment and the future railway system. Each section of ground was carefully scraped, leveled, and inspected under the supervision of engineering and surveying teams. Specialists continuously measured elevation and slope to ensure the line maintained the required accuracy across dozens of kilometers of natural terrain. Excess soil and sand were transported away from the construction zone by conveyor systems and heavy trucks. This process created a flat construction site ready for the compaction step. After the bulldozers finished leveling the ground along the railway corridor, the sandy soil still needed further stabilization before construction could continue. Engineers realized that adding controlled moisture to the loose soil would help the sand particles bind together more tightly, forming a denser and more stable base. Using water pipelines and long spraying arms, groundwater was evenly sprayed across the construction site, it allowing moisture to gradually penetrate into the layers of soil below. Once the moisture reached the proper level, engineers used the technique called dynamic compaction, where a steel weight weighing tens of tons is suspended from a crane and repeatedly dropped onto the ground. Each impact creates a powerful compressive force that helps the layers of sand and soil below become tightly compacted, forming a more stable foundation. Immediately after that process, heavy rollers began moving back and forth across the surface, compacting the ground to remove air pockets and lock the sand particles together. The deep rumble of the steel drums echoed across the construction area as each pass of the rollers transformed the soft soil into a flat and uniform foundation. By the time the surface dried again under the sunlight, the ground had hardened enough to support the weight of cranes, concrete mixers, and heavy material trucks. After the ground surface had been fully compacted, construction crews began spreading a base layer of soil along the stabilized sand along the railway corridor. Dump trucks continuously unloaded loads of the region's characteristic red soil from Kenya, which bulldozers then pushed and leveled across the construction site. This layer added additional weight to the sand beneath. It was evenly spread and repeatedly compacted with heavy rollers, forming a dense and solid base layer. Once completed, the surface was strong enough to support the weight of concrete beams and columns weighing up to 40 to 60 tons, which would later be installed along the viaducts and elevated railway sections of the line. On the reinforced and compacted ground, the railway bridge piers gradually began rising along the corridor of the line. These massive concrete columns were positioned about 35 meters apart, with each pier reaching up to 15 meters in height and weighing nearly 90 tons, depending on the terrain and structural load requirements. Across the entire railway route, thousands of concrete piers were constructed, forming long, straight rows stretching across the plains of Kenya. Each pier was cast using slip-form molds and reinforced with high-strength steel to ensure durability against high temperatures, strong winds, and the constant vibrations generated by passing trains. The spacing between the piers was carefully standardized to improve the stability of the viaduct structure and reduce the effects of thermal expansion. From a distance, these endless lines of concrete pillars extended toward the horizon, forming a vast framework of steel and concrete, the structural backbone of a modern railway gradually taking shape across the vast landscapes of East Africa. The next stage involved manufacturing precast concrete box girders, the structural elements that would connect the piers and form the bridge deck for the railway. Inside fabrication yards located near the construction site, steel molds measuring about 30 to 32 meters in length were precisely assembled to cast each girder. Within these molds, welded reinforced steel cages and pre-stressing cable systems were carefully positioned before high-strength concrete was poured in and vibrated to remove trapped air bubbles. After the concrete hardened, each bridge girder, weighing dozens of tons, was removed from the mold and transported to storage yards. Thousands of these massive girders were produced continuously, ready to be lifted and installed onto the bridge piers to form the elevated railway structure. Once the precast concrete girders were transported to the construction site, the installation of the bridge spans began. Heavy lifting cranes, or a launching gantry, a specialized beam installing frame that moves along the bridge piers, were used to lift each concrete girder weighing dozens of tons to heights of several tens of meters.